Hello everybody. Latte, little cream on top there. Mmm. Cream moustache. Right. 4.3. Should be easy, this one. So we've just got a UDL. And I'm going to represent the UDL, which would be, I don't know, 12 kilonewtons per meter. That value I will use to represent it by little w. Why little w? Because the weight of the UDL will be big W. Okay. So same jazz. Going to find first the deformation equation, and then second we are going to find the maximum deflection. So I am using well, first I need to know what my M equation looks like, so let's start off by working that out. So this is length L, that's A and B. Therefore I'm going to have a reaction at A and B. The sum of our forces in the y direction, you could just do this by symmetry, I suppose. So we've got RA plus RB. What's the total weight of this thing? Well, it's big W, but I don't want to use big W. So it's going to be little w times by the length. And that's going downwards. So little w times L equals 0. So that's one equation. Second equation, well, then we pretend that our UDL becomes a concentrated load with a weight acting through the middle. Take moments about A, say. Moments at A, go clockwise, and then that would give me, so what's the weight of my UDL? So that's little w times L. What's the distance from A? That's going to be half L, and that's going clockwise, that's positive. This one here will be negative from here to here, so we've got minus RBL equals 0. So therefore we can see that RB equals little w times big L. You see my L's cancel, divided by 2. I could have done it all by symmetry. Therefore RA, go back to equation 1, is going to be little w times by L divided by 2. So we knew that. So our shear force diagram is going to go up to little WL over 2. Now the next thing is to say, how is this thing going to drop? Well, it's just going to be a straight line, UDL, okay, and it ends up with that we're going to jump again with WL over 2 when we come to the end. So when we're at B, jumping up by the same amount, so that means we must be minus WL over 2. So start there, in the middle it's going to be 0. Draw a straight line there. So that's my shear force diagram. What is more useful, personally speaking, I would rather do this by maths and use the fact that I know that M, I'm going to call this Q graph, is the integral of Q with respect to X. If you don't want to do that, you could do that using the approach that we were doing with stress level 1, so I suppose I ought to do it that way, but that would be my preference, is to integrate this to find the bending moment equation, because basically I need a bending moment equation. Right, so to do that I will imagine that I'm taking a cut through the body. So that's my reaction at A, and I'll take the cut, go round clockwise, and then sum up moments looking left of me. So what have I got left? Going clockwise, I've got little WL over 2 times this distance from here to here, so that's an arbitrary x distance. So we're cutting through the beam somewhere, an arbitrary point, and that's x. And I've done something wrong, because why isn't that going to be negative? Okay, because now I'm going to do the UDL bit. So the UDL is the thing that's coming down here, and then you have to go for all that jazz. Well, where's the UDL? How far is it away from here to here? Blah de blah de blah. So let's start off with, if we take X section of the UDL, what is its weight? Well, first of all, which way is it going to be acting? So it's going to be, we know it's going to be a negative moment. What is its weight? Well, its weight will be W, little w, times by x. So that gives me the weight of the thing. So little w times by x. That's my weight. Now I'm going to take moments at this pivot point back to here to here. So what's this distance from here to here? Well, the total distance of the UDL that I'm cutting through is x. So the distance from here to here must be half x. Creamy. So we've got x over 2. Right, so that looks like that, although it doesn't. What have I done wrong? Why doesn't that look like that? No, why should that look like that? What am I doing? Slay, give me a break. Okay, right, so yeah, when x equals 0, we expect m to be 0, I suppose. And then when x equals L, we expect m to be 0 again. Does that work? Oh yeah, because we've got quadratic here. So there we go. L, and when x equals L, that becomes L squared over 2. When x equals L, that becomes L squared over 2. Right. If I did that mathematically, I wouldn't have any problems. So it should be when x equals 0, m equals 0. When x equals L, m equals 0. When x equals half L, that will give me x L squared divided by 4. Take away L a half times L a half, so that's L a quarter, times by, or rather divided by 2, so that's an eighth. So we've got a quarter, take away an eighth there. So quarter take away, I make that to be an eighth. I'm tempted to check on my calculator because it's late. I guess. So here we're going to be positive, and this is the maximum m that we're going to get, and that is going to be L little w times by L squared. Oh, I feel so unconfident. Point, I've got set x to be a half L times by a half, take away a half to the power 3. It's an eighth. Why am I doubting myself for? Okay, so that's what the M graph looks like, and that's what it looks like if we tidy up a bit. Let's put the leading x squared in the front, so that's going to give me minus little w over 2 x squared plus little w L over 2 x. Okay, now integrating the Q graph is a lot easier. There we go. Right, so I've got my M equation. I'm now going to stick it into here. Bring the EI up onto the left hand side, and then we want to integrate this. Okay, so you should be getting used to that by now. Always tend to bring the EI up, so we just got a nice sort of polynomial to deal with on the right hand side. Let's integrate this once. So that becomes minus little w x to the power 3 over 6. Integrate this once. Becomes x to the power 2 over 4 plus c1. Now here you could be naughty, and they aren't naughty in the book, so let's not be naughty, but we could say to ourselves, well, I do have a boundary condition. My boundary condition is that this is symmetric, everything's symmetric, the reactions here are symmetric, therefore I know the maximum, I know actually where the maximum deformation is going to be, and it's going to be in the middle, and therefore the gradient will be in the middle. Actually, let's be naughty, let's not follow the book. So we actually know a boundary condition. That won't always work. If we applied for UDL, yeah, kind of be the case, won't it? But you can get like distributed loads which are sort of like triangles, for example. So something like that, symmetry you couldn't use, but hey, why not? It's valid. So we know at in the middle, that's where L over 2, when x equals L over 2, that we've got a gradient. That's my first boundary condition, and I've got a gradient of 0. So let's substitute that in there. So minus w over 6 L over 2 to the power 3, and then I've got plus WL over 4, and that will be L over 2 squared, plus C1. So therefore C1 equals, well, we're getting the common factor of WL cubed. Yeah, so the first one is minus 1/6 times by a half to the power 3. It's beautiful, isn't it? Plus 1, whoops, it's not good, plus 1/4 times by a half squared. Right, so that's this term here. So we want the negative of that, minus 1/24. And this term here is WL cubed. Yeah, L cubed. Right, so that's the C1. We're now going to substitute that into here, and then we're going to integrate again. So I'm going to pretend I've already substituted, and then that's integrate. So that becomes, the first order differential becomes a y. Integrate this term here. That becomes minus w x to the power 4. 4 times 6 is 24. Plus WL x to the power 3. 3 times 4 is 12. Minus 1/24. WL cubed, so that's a constant. So that's x, and then we get our second constant. So notice this problem is, because I'm using my brain, probably not a good plan, is actually giving me more boundary conditions than I actually need. So I have two unknowns. The boundary conditions I'm going to end up applying, and what I'll do is I'm going to use my last boundary conditions as a check. So the boundary conditions I'm using is that when I'm here at the start, y equals 0. When I'm here at the end, y equals 0. Okay. And the other one, first boundary condition, is this one here, that the dy by dx equals 0. So I've applied that boundary condition there. So I'm going to use this one, and I'm going to use this as my check. So using this equation here, let's apply this boundary condition. Why? Because when we put 0 in there, loads of things are going to cancel. So we have EI times by 0. I don't want to make it look like a function. So times by 0 equals 0. So the left hand side becomes 0. Right, 0, 0, 0. Yeah, 0, 0, 0 equals C2. That was easy. C2 equals 0. So we've got our equation here, and what I'm going to do, so that was my I should tell the reader what I was doing there. So boundary condition 2 is y when x equals 0, y equals 0. Okay. And then what we'll do is we'll do boundary condition 3 as a check. So boundary condition 3 is when x equals L, y equals 0. Is that the case? So we've got EI y set x equal to L minus W L to the power 4 divided by 24 plus W L to the power 4 over 12. Take away W L to the power 4 divided by 24. Right, so we substitute it in there. Remember C2 is 0. So put the x equals L, x equals L, x equals L. And what do we get? Well, we can see we get 1/12, take away 2/24, so I make that to be 0, so the check works. Alternatively, we could have used that boundary condition to find probably we'd probably use that to find C2, I guess. No, we'd probably use it to find C1. Right, okie dokie. Where are we? So we found this equation and we've checked that it works. Now let's find the maximum deflection. Well, we know that's in the middle. So what we want to do now is take this equation, remember the C2 is 0, take this equation, and we want to set L to be half, sorry, we want to set X to be half L. So that gives me EI. Since I'm looking for deflection, I'll take my EI over to the right hand side this time. So X equals L over 2, 1 over EI. So I need to put that there, open a bracket, and now start substituting it all into this equation here. Okay, so leave it there, that works. So we've got minus W over 24, L over 2 to the power 4. Then we've got plus WL over 12, and that's going to be L over 2 to the power 3. Then we've got minus WL cubed over 24, and that's going to be L over 2. Close the bracket, close the bracket. Remember my C2 is 0. Okay, so obviously we can see that we've got L to the power 4, L to the power 4, L to the power 4, okay, and WWW all the way through. So now we've got W L to the power 4 over EI. Let's put the rest of stuff in our calculator. So I've got a minus 1/24 times by a half to the power 4 plus 1 divided by 12 times by a half to the power 3. Take away 1/24 times by a half. So that leaves me with minus 5,384. So rewrite that to be minus 5WL to the power 4 over 384 EI. Okie dokie, and that is the correct answer. So that's that bit done.